I will ask now, we are just on time for our fifth panel of today, and I will welcome to the stage now Pooja, our great moderator for today's session. Great.
Hi, everyone.
Hi, Pooja. Great to see you. And Pooja Vadva is in her final year of PhD at University College London, UCL, where she focuses on synthesis and characterization of solid electrolytes, as well as the electrochemo mechanical modeling of solid-state batteries. So she's an expert in the subject matter today, and she previously interned at Tesla, where she focused on battery degradation modes, and at Jaguar Land Rover in the advanced battery team. She's also a battery consultant for Battery Associates and Intercalation Station. So welcome, Pooja. Thanks already for moderating this great session. And with that, let's welcome everyone else on stage. Wonderful. And I hear that Donald may be have a bit of delay, so we will start and he will hopefully join us soon. Pooja, the floor is yours.
Thanks. Yeah, I'm really excited for this panel today, discussing solid-state battery announcements. I think we'll be covering a lot of industry as well as academia hot topics. So I think, yeah, it'd just be great if the panelists, maybe starting with Maria and then Raymond, just introduce yourselves, I guess, your area of research, or I guess for Raymond, industry. And then maybe just for the listeners of interest, what kind of got you into batteries? So Maria, if you want to start.
Thank you, Pooja, for the introduction, and thank you everyone for the organizers for the invitation. So I will start briefly explaining my background. I'm here today because my research topic is devoted to solid-state batteries, mainly polymer electrolytes for lithium metal batteries. I'm coming from CIC Energy Gune, a research center in the north of Spain. We are devoted to the different research topics in the field of energy. And in my case, as I was mentioning, we work towards the deployment of polymer reeds or hybrid electrolytes for lithium metal batteries.
Very good. Shall I go next?
Yeah, go for it.
Yeah, sure. Raymond Carver, my name. I'm the head of application engineering for Factorial Energy. Factorial Energy is a US-based startup. We're located in Boston, working on solid polymer electrolytes using lithium metal anodes. Myself, I'm a chemist by training. I spent a couple of years at BMW in Munich. And yeah, I was always driven by working towards an application. So when batteries is obviously very close to it's already applied in the industry. So yeah, thank you so much for having me, and looking forward to an interesting discussion with you all.
Yeah, thanks both. So we have industry and academia experts, so that's great. I guess the first question that I wanted to ask you guys is, with solid-state batteries, we have different types of solid electrolytes. Primarily, it's kind of oxides and sulfides. So oxides kind of, have a brittle kind of chemistry, and their ionic conductivity can be a little higher. So that's like one of the advantages. But the sulfides also have a high ionic conductivity. But I think LLZO is one of the oxides that are used, and its stability with lithium metal is like a prime advantage. For sulfides, however, they're kind of softer, and then we think that it could be easier in terms of manufacturing. So I guess I just wanted to ask from you, or if you have different kind of chemistries, what do you think would be better for solid electrolytes? And then specifically in terms of ease of manufacturing, I guess safety, cost, and degradation. So maybe we start with Maria.
Okay, so if in this case we are considering solid electrolyte and we are just covering these oxides and sulfides, it's clear that, as you were mentioning, there are several advantages and disadvantages in both cases. I think that from the oxides point of view, due to the brittle properties of these materials, the manufacturing might be the main disadvantage. On the other hand, if we move to sulfides, we improve the mechanical properties. That could be an advantage for manufacturing, but then on the other hand, we need to consider the safety issues related to the sulfides due to the instability or the reactivity with the humidity. So this might be a very risk concern. Part of that, I think that moving, I will move slightly apart of these two materials. So if I need to think about which will be the real material that will be in the market when we consider solid state batteries, I think that it's not going to be only one, the one that will provide the best properties. I think that at the end we will need to move to hybrid materials, because the different components that we may find, or the different families or chemistries of materials, offer at different levels advantages and disadvantages. And I think that Raymond will agree also, because he was mentioning he's coming from the polymer side. So I think that at the end we will need to balance the properties of the different materials to make the best of this type of composites or hybrid electrolytes.
Okay, that's really great. So I guess just following on from that, then the polymers side, I think Raymond, maybe you can speak to that a bit more.
Oh yeah, sure. I fully agree with Maria. So I actually spent my PhD working on sulfide salt electrolytes, and now with Factorial, it's more on the polymer side. So I think I'm fairly familiar with the two systems. I think it all comes down to what Maria said, that there will be multiple materials that can succeed, but the materials have their trade-offs. And I think especially the two full solid state systems that you named, Pooja, they of course have little flexibility. So I think when you consider a solid state battery, especially with the lithium metal anode, you always have moving parts in the system. And this is of course easier compensated when you have flexible components such as a polymer inside the battery. And I think this is also one of the one of a couple of reasons that that's all solid state batteries suffer today, or what hinders them to go into the market.
Yeah, that's really interesting. I guess one of the disadvantages with polymers is the low the low ionic conductivity, and then mixing it with the oxides and sulfides, you can get that advantages. So that's really good. Do you see any downsides for polymers in terms of like maybe degradation or side reactions, because you're kind of having this hybrid approach?
Mm-hmm.
So I think the question was towards me or towards Maria?
Both of you, I guess. Raymond, you can go first, and then Maria.
Okay, so as you said, Factorial is following a more hybrid approach. So it's not like a single component system, which makes it's a very complex system, but it also has a lot of functionalities. So as you mentioned, there's the connectivity, but there's also like the interface stability as well as mechanical components to it. So it might not be always just a single electrolyte that will deliver the best performance for your battery.
Yes, I mean, following the comment from Raymond, I fully agree with this. And I think that polymers, of course, we were discussing or mentioning before the advantages by means of processing, because of the flexibility. For example, we could go for easy manufacturing by dry process extrusion, for example. But on the other hand, as you are mentioning, Pooja, we have the disadvantages that we may face because of the degradation of the instabilities with the electrode. But at the end, also the polymers, they offer a wide variety of chemistries. So it's really on the side of going to the design of a chemistry or a tuned chemistry to make sure what we are looking for. So the stability of high voltages, that is one of the main disadvantages that has been widely reported related to the use of the polymer electrolytes. But on the other side, we need to consider also the stability of with the lithium metal. So at the end, as I was mentioning before, and Raymond was saying, so when you have a hybrid, you have different components, and you need to finely tune the properties of the materials that you select according to the technology that you are developing. So there's not going to be one unique electrolyte that might be working with different electrodes or for different technologies. So I think that this is something that we need to consider when we select the components or the chemistry of the electrolyte.
Yeah, thanks. That's really great, really insightful. So I guess leading on from this, we're really focusing, on the lithium metal and the reactivity of the lithium metal. Firstly, there's some challenges with, just manufacturing lithium metal. We have shortages of lithium in the first place, so mining and cost is an issue. And then how do we even kind of manufacture these lithium metals on the anode side? So I think there's been a lot in academia and also in industry. I think I can speak to a few companies like QuantumScape that use this like anode-free configuration. So this is essentially where there is no lithium on the current collector, and then it's kind of formed in situ on the charge, where all the lithium is kind of coming from the cathode and then forming onto the current collector on the anode side. So that's one way of doing it. But I guess you still have issues with dendrite formation and kind of lithium metal. And then another approach, which is I think what at least academic papers, especially, and I think some industries like solid power are moving to, is having a silicon anode, so that your instability on the anode side there is kind of removed. So maybe other metal alloys or any other things that you think or could comment to from the anode, like should we be fixated with just using lithium metal? Maybe this time, Raymond, you can go first.
Yeah, absolutely. I think for what you mentioned about silicon, I don't think it's granted that there will be no reactions. It will highly depend on the electrolyte system that you're using. And then I think ultimately what you said is that the system should have no excess lithium. So of course, everyone's that is working with lithium fall is trying to minimize the additional lithium that the system will need. However, of course, it's not only about the energy density and the cost. You have a couple of other parameters to consider, which is, for example, power densities that you can run and the cycle life. And those are very heavily impacted, of course, by the choice of the anode. So I think it's also about speed to market. So I think that there are, of course, some good approaches about going completely lithium free. However, it is questionable if those approaches will be market ready in the time needed.
Yes, I agree, and I think that maybe lithium metal, in spite of the several disadvantages, let's say, that we may have related to the reactivity of the interface or the stability, I think that is closer to be in the market if we compare to anode free, so to anode-less technology. So of course this will be the best if we consider also power and energy density. But at the end, again, we will have still lithium metal, so the safety concerns related to the lithium metal will be there. And then related to silicon, even if we consider that the main issue of lithium metal is the instability or the reactivity, I think that with silicon, we are going to face also several challenges, like volume expansion also, and the stability of silicon anodes. At least even if there are many papers or at the academy, there is a lot of work going on this topic. I think also that still lithium metal is the main candidate for going into the solid state batteries into the market.
Okay, that's interesting. So I guess you're both voting for lithium metal on the anode side. Do you think that from like a supply chain issue or manufacturing of lithium metal, that could be one of the challenges? Yeah.
I think that if we consider the price, lithium metal, of course, in this case, we should move to other alternatives and discard lithium metal. And also for the manufacturing, all the gigafactories that now are betting towards lithium metal, I think that they need to readapt all the manufacturing process for going from lithium ion to solid state, because in this case we will need to face a new challenge that is the handling of the lithium metal. But I think that in this regard, maybe Raymond, that he's closer to the industry, may provide better insight.
Yeah, I think of course we're in some very turbulent times right now. So what you described may not only affect lithium metal, but also nickel, cobalt, and pretty much every material that is used in a battery today. Regarding manufacturing, the industry is definitely catching up. I think a couple of years ago, it was impossible to get thin foil in reasonable quantities, but there have been some emerging players that can supply large quantities of lithium metal with sufficient quality and quantity and thicknesses and so on. So that's very good to see. And I think this is something which we will also see in the future to be more emerging.
Okay, great. So I guess following on from that, Raymond, you may be a bit biased working for Factorial Energy, but which kind of market leader do you see going to be quickest to market at the moment? I think there's a lot of time frame, some companies announcing mid-2020s, but I guess from your standpoint, like when you think about the different chemistries, so QuantumScape is kind of working on a solid electrolyte anode free, solid power, more like looking at silicon. And then Factorial, which is kind of like a mix of like polymer. So they're all looking at different chemistries. So I guess in your opinions, which one do you think would be easiest to manufacture or quickest to market?
Yeah, I think maybe not so specific on the individual peers, because there's a lot of also existing cell manufacturers out there that are following those routes. But overall, I would differentiate between all solid state and something like what Factorial is doing, like a semi-solid state approach. So I think if you can, of course, use much of the existing equipment that is in place for lithium-ion batteries, and where a lot of capex is now going into, that this will, of course, drastically accelerate EO speed to market. So I would expect, and I know I don't want to sound too biased, but I think hybrid systems will have an easier way into the market, and also will be more short-term than will be all solid-state cells, regardless of the anode configuration.
And on that note, let me just use this as a segue to show the result from the poll that we launched some time ago regarding solid-state batteries and the public's view on the how optimistic one ought to be in terms of commercialization. So if maybe at this point the panelists could tell us their thoughts on whether they think those answers are accurate, with almost 50% assuming that commercialization is possible before 2030 compared to 2025 or earlier. Any reactions on those results?
Yes, I think that I have not participated on this, but I will agree with the 48%. I hope that before 2030. I think that saying before 2025 might be quite optimistic. I think that there is still a lot to do on this regard, but I definitely will say before 2030.
Yeah, I think there's a huge spread, of course, here between the different answers, which might also stem from it's not really clear what is meant by commercialization. So maybe there are some announcement about demo cars or about like demo fleets and so on, which might sound like it's like ready for full deployment, but it's not. So I think I would agree with what's shown in the graph here before 2030. It's great to see also that it's not like always the next decade. So, but we're actually like getting closer and closer, and we see a lot of efforts in ramping up the capacity for solid-state batteries. So I think we're on a good track here.
Yeah, I definitely agree. I think actually one of the big challenges is, in academia, definitely on the cell level, getting something to work can be challenging, and then trying to actually manufacture that at scale is another problem as well. So yeah, I also agree with before 2030s would be great to see something. So I guess, yeah, moving on from that then, do you see that solid-state batteries will kind of dominate over lithium-ion market, or would they be used, for separate like niche applications? So I think what we see in industry is targeting, for this high energy density, probably initially quite high cost as well. Maybe for electric vehicles, with longer range or luxuries, maybe even eVTOLs. So these are electric vertical takeoff and landing, like air taxis, which look quite cool. So do you think that initially that this will be probably deployed in these kind of segments? And how do you think that will kind of play out? Like, will there be advantage beyond just the high energy density of solid electrolytes, for example, for eVTOLs or for cars, if we're charging them or discharging them in or driving them in low temperature conditions, would there be an advantage of solid state over lithium ion? Maria, maybe you can start.
So the main selling point for solid state, and I think that is something that we are looking for, it is the safety. So compared to lithium-ion technology, so of course the energy density is one of the targets, but also safety. And this is something that at the end, even if we all agree that solid electrolyte might be safer compared to liquid electrolyte, this is something that we really need to prove in a device. Because if we consider that we still have lithium metal on the anode, there is still some reactivity and safety concerns. So one of the main advantages, I will say, that will be safety. And then by means of application, I think that solid state is not going to fully discard lithium ion. I think that at the end, there is going to be market for the different technologies and applications, because now we are in a race where everyone wants to be the first one delivering the proof or the prototype for the solid state technology concept. But it's not a question of which is going to win this race or which is going to be first, because there is a really huge demand. So I think that we really need to consider to have different technologies, and of course for the different applications that we will have in the market.
Yeah, I think I would say that solid-state batteries probably have the potential to dominate lithium-ion batteries, but maybe not as we know today, because I think solid-state batteries right now, they are aiming at maximizing the energy density by the use of lithium metal. But even today's lithium-ion batteries are usually purpose designed. So you have cells that have a very high loading for high energy density, or low loading for high power, or LFP for low cost. And I think we will see some similar development also for solid-state batteries. So it might not necessarily be always lithium metal on the anode side, but there might be some other derivatives that then fit the individual segments of the market. This will take, of course, some time. I don't think it's development within like 1 year or so.
Yes, I think that as we were discussing before when we were showing the results of the question when are going to be solid state in the market, I agree with Raymond that even if we say before 2030, maybe this is not going to be really in the market, maybe some demonstrators. And also, as you were saying, Pooja, it's not the same, the research that we do. For example, in our case, that I am leading a group in a research center. Of course, when we conceive a new material, we always need to have in mind the final application and how feasible will be to scale up this. But there is a period of increasing the TRL level of this development. So from the lab scale or from a concept to finally have this integrated in a battery and of course in an EV. So I think that this might take several years.
Yeah, no, that's very interesting. I think, yeah, it was really interesting to hear from Maria as well. The kind of solid state advantage is the safety. And I kind of wanted to talk about that a little further. I think solid state, they don't have the flammable liquid electrolyte, and that's one of the reasons that we kind of say they're very safe. But I've seen a lot of academic papers actually trying to look into this a bit further and trying to probe the safety a little bit more, because if you short circuit even a solid state cell, there's going to be a large exothermic reaction which produces a lot of heat. And even though there is no flammable electrolyte, which is still debatable because sometimes some solid electrolytes that have an oxide sometimes put like a small amount of liquid electrolyte between the kind of interfaces, especially with the cathode, to improve that stability there. So even if we assume there's no flammable liquid electrolyte, there's still a lot of heat generated, which, if the cell has some metal encasing, that could cause it to kind of get really hot and melt. So I just wanted to know what are your thoughts, Maria, I guess from an academic standpoint, the kind of recent interest in this, and then maybe from Raymond more on like the cell impact side, maybe some safety things that you're trying to put in place, if you can talk about that.
Yes, sure. So as you were mentioning, even if we consider solid state in many of the cases and many of the examples, people claim they have solid state, and for that reason the battery will be safer. But I was going to say most of the cases, but let's say in many cases we still have a liquid component, and even if we have a solid, this solid can be flammable also. So to really say that we have a safe electrolyte, this has to be proof in a device, because considering the academia, we test the safety of the materials, let's say focus on the electrolyte in this case, by different means. For example, we check how is the thermal stability or the flammability test. And in this case, you may see that it's safe or that there is not fire, of the temperature for decomposition is really above the target for the manufacturing or for the use of the battery. But then when you transfer this to a bigger or scale up to a bigger prototype, then there are many other issues that we need to consider to evaluate the safety of the battery. And I think that on this type of testing or on this type of concerns, maybe Raymond can provide the input from the company perspective or industry.
Yeah, sure. I think I totally agree. So it doesn't, just because you have a solid electrolyte, it does not imply that the battery has to be safer. But it's also the same vice versa for liquids. So just because you have a liquid doesn't mean it's unsafe. I think it highly depends on what the materials, especially thermal properties, are. So if you can increase the thermal stability of the electrolyte over of the one today, I think there's a lot of potential for solid-state batteries or semi-solid-state batteries to actually be safer. Not because they will completely avoid this thermal runaway, but the biggest fear in the automotive industry is usually the thermal propagation. That means you have one cell going off and then the whole pack following. And of course, if you have a higher thermal stability, this will affect the second next cell more than maybe the one that is having an incident. And I think this is something that might be overlooked a lot of times, that maybe even like a little improvement on the thermal stability might be very beneficial for the full pack design.
Just on that, so now we'll take a question from the public, and again, just a call to everyone who'd like to chime in to send their question on the chat. So one question that we received was, how would the recyclability of solid-state batteries compare to regular lithium-ion batteries? Really great question. So I'll let maybe Maria answer first, and then Raymond.
And yes, I think that this is a really key point during the development, and something that should be evolving at the same time with the design of the solid-state batteries, considering the recyclability of the materials that we are using within them. So again, I will move to my specific topic, that are polymer electrolytes for lithium metal batteries. So this is something that we are now trying to develop, how feasible will be to process and recycle these cells. So the good point from the polymer side, of course, it depends on the chemistry that we are thinking about, is that it might be recovered by just using different solvents, because it might be dissolved, and then we could recover both the polymer and the lithium salt or whatever that we are containing on this part of the electrolyte. Then we will need to look at the lithium metal and the different possibilities, because it could be also recovered by different means. But compared to lithium-ion batteries, I think that if we move to oxide or sulfides, in that case, I'm not really an expert on this field, so I'm not really sure how feasible will be in a short term to consider the recovery and the recycling of these materials.
Yeah, I would say that generally there will still be need to recycle solid-state batteries overall, because they share a lot of the precious materials that are used in lithium-ion batteries as of today. But also with the variety of materials that we just discussed, it's hard to comment generally on solid-state battery recycling. You would have to be a bit more specific on the exact chemistry or technology. However, then, especially with lithium metal anode, there's of course the desire to also recycle the lithium. So it's not only the cathode material that is worth recycling, but it's a field that is still developing. So there's not, at least from my point of view, I'm not aware of too many processes that are in place for solid-state batteries. It is something, of course, that we are also internally working on, but I can't share any details on the exact routes here.
Yes, I think that this is really important, and the companies or the gigafactories that now they are going on this rise on the development of this solid-state technology should run in parallel the research of how feasible will be to recycle the components that they are putting and they are developing within these batteries, in order to be prepared and be ready once they are in the market.
Yeah, I think that's really interesting. So I think moving on to that, and I want to talk about the cathode materials. So this is kind of overlooked a lot of the time. We're focusing on the anode side, lithium metal or silicon anodes. They have 10x the theoretical capacity of graphite. So you're not going to be limited on the anode side when it comes to cell capacity. So then your cell capacity is limited from cathode. So right now, the kind of cathode materials we have is like NMC, and if we can go to even higher energy density, so looking at perhaps nickel-based or manganese-based, incorporating some of those materials. And the advantage of the solid electrolyte that we have is that we could go to higher voltages. So liquid electrolytes kind of degrade at these higher voltages. So that's one of the advantages that we have. So first, I guess, is two parts to this question. Is just, what do you think about the different types of cathode chemistries and additional kind of cost for that? And then I think linking to the second part of the question, which is also came from the audience, from Raghav, is how about like lower tech, so cheaper solid state cells? So maybe the pairing with sulfur cathode, I've kind of seen a lot of, and sulfurs have a lot of issues with liquid electrolytes, but using a solid state system, we can kind of stop some of the effects. So what do you think in terms of solid state being for the high energy and expensive, the high voltage cathodes? And do you also see a market for sulfur or even, LFP cathodes on the kind of cheaper side? Maybe Raymond, you can go first. Maria.
Yeah, sure. So maybe to answer the first question, I think for the cathode material, we will see a similar development as for lithium-ion. So different cathode chemistries for different segments or different costs. So this will be NMC, LFP, and so on. As you said, Pooja, with the higher voltage stability, this of course enables a lot of other cathode chemistries. But there it's more on the material development actually for the cathode materials rather than on the solid electrolyte side. So there needs to be some more material development to make sure that those materials are itself stable, that they can maintain the structure over multiple cycles. And regarding the audience questions on lower tech solid-state batteries, I think, of course, with solid-state batteries being highly innovative and disruptive, we will, of course, first try to achieve cost parity with lithium-ion batteries, whereas the lower tech usually aims to be even cheaper. I think introducing a chemistry like that, which is initially cheaper, will be really difficult, at least on the cell level. But I totally see potential for LFP, so absolutely. Lithium sulfur, not so much because of the energy densities that are needed for automotive applications, which is what we are, of course, very much focused on. So there might be other applications where this will fit into more better.
Yes, so I agree with, do I continue with this question? I just see that there's, okay, here is the question, sorry. Yeah, so I agree that when choosing the cathode material, we need to consider the price and the application, because of course we have LFP that might be cheaper compared to NMC cathode material, but of course then we go back again to the energy density. So at the end we will need to balance, and there will be market, as I was mentioning before. I think that there will be market depending on the application for all the type of cathodes. Also we need to consider not only the energy density at the price, but also the supply value chain. And currently I think that LFP is mainly dominated by Asia. I do not think that in Europe there is a lot of manufacturing of this active material. So this is something that we will need also to consider. And regarding lower tech, so in our case, at CC Energy Gune, we are also working on lithium sulfur, mainly for liquid electrolyte, but now we are also trying to tackle the several issues that the lithium sulfur technology faces with this type of electrolytes. And somehow we can say that it might be slightly diminish the issues that we face, but of course we still have a lot to do on this regard. So I will not say that it's ready to go into the market. And then again, we should need to look for other applications, because if we focus on EV, we should choose other type of materials rather than lithium sulfur, mainly nickel-rich cathode materials.
Great, thank you both. And we have some great questions coming in the chat, so that's really great. Yes, we could start with Marcus' question around the strategies that are present today to overcome the interface challenges between the cathode and separator and anode. So if Raymond or Maria, you want to jump in, feel free to do so.
Yeah, I would just quickly like to add to that. There's different, obviously, interface methods to improve the kind of solid-solid contact between the cathode separator and the separator and anode. I've kind of seen some that I'm actually working on in my research group, and I think someone else also put in this, Amrit, in this chat. What do you guys think about like glossy materials? So materials that kind of have kind of plastic deformation or kind of similar to polymers, but that have like our inorganic materials, so they'll have higher ionic conductivities, and that could kind of improve these interfaces. And if you have any other suggestions that would help with this.
Okay, do you want to go first, or? Oh, I can answer, of course. So I mean so first maybe the audience question. I don't think the use of a solid electrolyte will completely remove any interface or any interface design. So there will be still strategies in place to protect the interfaces, like cathode material coatings or lithium metal coatings that are especially designed to make sure that those particular interfaces are more stable. So I think especially on the cathode side, it's very similar to lithium-ion batteries. It's just a very good, straightforward strategy. And regarding the glassy materials, I mean, of course, with the hybrid system, it's not we're not talking about a crystalline polymer. So, but maybe this is more on the sulfide or oxide side. But I think, of course, at least industry would like to have processes in place which are highly controllable. With glassy materials, it's really hard to predict the properties of the electrolyte, which makes it difficult to design the process. So I think it's inherently more challenging. But I agree that there are some interesting combinations that usually, especially for the sulfide, the conductivity is much higher compared to the crystalline counterpart. So yeah, it's very, very interesting topic for research. Maybe Maria can comment more.
Yes, so first going to the question of the audience, or combining both of them and focusing on the interfaces, I think that this is one of the main challenges that we need to face when we are talking about solid state batteries. Currently at CIC, we are leading a project, European project related to these different interfaces, because we not only need to consider the interfaces that we have between the electrode and the separator, also even within the electrolyte, when we have a type of hybrid material, we will have even further interfaces that we need to control to make sure the stability among all the components. And in the case of the electrolyte by itself, the stability with the electrode, so with the cathodes first, I think that this will depend on the type of material that we are using. Of course, if we are talking about oxides, there will be more stable to high voltages. If we are talking about polymers, we will need to consider this depending on the cathode that we are using, mainly where we are considering high voltages. And focusing on the lithium metal, of course, there are many different techniques that are being developed in order to provide this overcoating strategy on the lithium metal to improve the contact and the stability with the electrolyte, independently on the chemistry that we are selecting for the electrolyte. But also something that we need to consider and that we may consider is the use of the additives by itself contained within this electrolyte in order to improve the SCI over the lithium metal. I'm talking always about lithium metal, but this, of course, will be extrapolated to different type of anodes, because in silicon we will face also several challenges at the interface between the silicon and the electrolyte.
Yeah, that's great. And how do you, I guess this next question from the audience, would it be difficult then to separate the metallic anode, I guess, from the solid electrolyte? I mean, even if we have like a solid polymer electrolyte, even oxide systems or sulfide systems, this can be tricky, especially in academia. We often apply, or I think even in industry, we apply a lot of pressure to these solid systems to kind of improve the contact between the interfaces. So I guess when you're trying to separate, perhaps for recycling, then this could be an issue. What are your thoughts on this?
Yes, from my experience with polymer electrolyte, of course, in many cases, if we don't consider the EV application, for other applications, we need to increase the temperature in several battery systems based on this type of solid polymer electrolyte. And of course, later for the disassembly, and if we consider the recovering of the different materials and the recycling, this will be a really challenge to separate from the metallic lithium metal. But there are other type of polymers that, despite this pressure that we need to apply for the cycling, later might be easier to get recovered. And of course, I think that if we consider this difficulty of separating the different components for the recycling, I think that solid state battery, what we need to move forward and consider and look for the strategies for the recovering of the different components. For example, as I was mentioning before, maybe trying to dissolve, play with the properties of the different components. Maybe some of the materials could be dissolved, melted to be recovered. So I think that this will depend also, again, on the type of technology or the type of electrolyte. It's very difficult to say, to cover solid state electrolytes as a whole, because there are many different variables, many different type of chemistries, and it's difficult to apply the same procedure or define a general protocol for all of them. So I think that at the end needs to be something specific, depending on the type of electrolyte that we are talking about.
Yeah, I think maybe referring to the question, it would be, of course, interesting to understand where it's coming from, if it's more from a research point of view or recycling. Because of recycling, we don't need to delaminate individual layers, because we're looking at cell stacks with 40 plus layers. So I think this is more an R&D related question. I think it's of course it might be more difficult to analyze, but there are surely some more sophisticated in situ methods that can be applied to still look at the polymer interface. That being said, I think the other salt electrolytes, it's not. It doesn't say it's much easier to really separate the interfaces when you have any powder or any sintered electrolyte on top of a lithium metal anode. It's still very hard to monitor, to analyze solid-solid interfaces. So I think in this case, it's easier to do R&D on a liquid-based system.
Okay, that's great. I guess then just, I think we have around 5 minutes left. I think I just want to ask you a personal opinion. What do you think are the biggest challenges in solid state, and which companies or which type of technology do you think would probably be, one of the biggest disruptors in this space? So I think just give my opinion as well is I think what Maria mentioned on this as well is the lack of standardization, especially from an academic point of view. I definitely see, trying to compare different metrics, and it's quite difficult for the different solid electrolyte systems when we have different standardization. And I think for anything to kind of scale and move into industry, we need to have that in place. But yeah, it'd be good to hear your comments. Raymond, if you'd like to go first. And also any closing remarks that you have.
Sure. I think you raised a very good point. The standardization would be in favor, especially in terms of cell format, because as of now, many OEMs use very different formats, even for different vehicle lines. So you cannot really one-to-one replace a battery, at least not today. And then I think challenge regarding solid-state batteries is also the volume expansion. So this is something that we need to be more focused on the system integration, not necessarily on the chemistries. I think chemistries, there are some very good ones out there that work fairly well. But I think the system design around it is something that has to be looked at.
Yes. So I think that regarding the challenges, I agree with everything that we have discussed already within these 45 minutes. So I will go more to the closing remarks. So I think that from my point of view, I will be really happy to be part of this development and this change from to EV vehicles, including these solid-state batteries, mainly highlighting the energy density, the safety, and also to spread their use and the transition to greener energies. And considering what you were mentioning about who will be first on the market, on what will be the one reaching there first, I think that, as I was mentioning before, I will not consider a race. Of course, there is a lot of investment and interests from the different companies. But I will say, so from a scientific and research point of view, that there is room for everyone, and should be more about the collaborative work in order to get there, and having in mind that the high demand of energy will allow everyone to be there. And also I think that what you mentioned about the standardization is also a critical point, very important.
Oh yeah, I totally forgot about the speed question. But I think ultimately the best team will win, right? So this might be also one of the biggest challenges, to get the right talent and have the right people working on what we need to focus on.
Yeah, I'm surprised you didn't say factorial. No, yeah, that's really great to hear. And I guess for our audience, do you see kind of a lack of kind of people in this space or working, or do you think there is definitely a need for this, and what type of backgrounds would be great? Like, is it academic routes? Is it apprenticeships? What do you think?
I think that there. Sorry, Raymond, go ahead.
No, please.
Okay. So I think that we need to combine different backgrounds of people. So people, of course, with the vision of the industry to establish the requirements and the real needs, but also people coming from the academia that can have breakthrough ideas, because even if there is a need of reaching the market really fast, I think that at the end we need to consider this a long period development. So we will need always some people going forward, moving forward, and developing new chemistries and new materials to afford the next challenges. So we will arrive maybe hopefully before 2030, but then there will be a new challenge to be faced, and the demand and the requirements will be higher. So I think that really combining these two words will be the best way to reach the targets.
Yeah, I think that what you said is absolutely true. And it all comes down to diversity. So we actually recruit a lot of people that are not straight from the battery industry. I can only encourage you to apply, because, of course, if we only take people from a large cell manufacturer and we just rebuild the team with a different logo, we won't be as innovative as we are today. So it's really about combining the right people from various industries that can bring some new and fresh ideas to the team, and are really willing to take up this challenge to compete with the very largest companies out there.
Great. Well, with that, let me thank all three of you very warmly for this great panel. It's rare to have such an advanced and on-point conversation on this topic. So really thank you all so much for participating today. We talked about so many topics, from safety to standardization, and you offered a much clearer picture of solid-state batteries and the road ahead. So thank you to the three of you. And this concludes our fifth panel of the day. We are now opening a networking break, which will last for 15 minutes. And the next panel will be happening 15 minutes past the hour, so 6:15 Central European Time. And that sixth panel will be tackling the topic of policies, battery policies, with a focus on the US, including the Inflation Reduction Act. So be sure to join us then. And meanwhile, just click on the people section on the left-hand side of your screen, and you'll be able to connect with battery professionals worldwide. So looking forward to seeing you on our next panel. And thanks again to our panelists today. See you soon.